Good morning, Dr. Johanna and everyone. We are Group 10, come from SETG 2741. Our topic for second experiment is flow measurements. My name is Yee Wei, and my group members are Sree, Syahidah, Pik Lin. These are our contents in our presentations. First, let's start by looking at report summary. This experiment is done with the flow measurement test bench. Through the applications of Bernoulli's principle, the relationship between flow and pressure is determined. It was found that when the flow rate increases, velocity will increase and the pressure will decrease. In this experiment, we need to carry out several precaution steps to get more accurate data. Then the rotameter reading is set slowly to the value where the manometer reading shows that the maximum and minimum reading, which is the height difference, will be the largest. Then we gradually adjust the rotameter to 200 liters per hour. The procedure is repeated for orifin plan, nozzle, and venturimeter. From the data analyzed, we can compare in different equipments. We have found venturimeter is the most accurate measurement because the discharge coefficient is applicable and less but close to 1. Next, the objective of this experiment is to compare the discharge coefficient of different types of flow measurement method. Next, I will move to the introductions of flow measurements. Flow measurements are easily found in our daily life. People can find the flow measurements on their water tap meter that count how much water that they consume in their house. Furthermore, a flow meter is used to calculate the flow rate of the fluids or energy to allow the process to be monitored and to ensure the final product is of the required quality. The principle of the flow meter is based on the change in the static pressure or pressure drops. Hence, it can be related to the change in velocity is affected by the change in cross-sectional area of the flow of fluid. Next, I will explain the theories. In Orifin's plan, restrictions with an opening smaller than the pipe diameter which is inserted in the pipe. Due to the smaller opening areas, the fluid velocity will increase and causing a decrease in pressure. The flow rate can be calculated from the measured pressure drops across the Orifin plan. Bernoulli equation can be applied with the assumption of the flow is horizontal, steady, inviscid, and incompressible between the point 1 and point 2. The equation for the theoretical flow can be expressed as following three equations. Below is the explanation of each symbol. Okay, the nozzle apply the same principle and calculation as Orifin plan. The only change is cross-sectional area of nozzle. The difference between the nozzle and Orifin's plan is the shape of the restriction openings, whereby the nozzle is approximate a quarter ellipse. The venturi consists of rapidly converging sections denoted as the point 2 in the picture, which increase the velocity of flow and reduce the pressure. Then it returns to its original dimension of pipe. This is a particular accurate method of flow measurements as energy loss is very small. Some principle and calculation as previous ones, with the only change is on cross-sectional area of venturi.
So I'll be explaining about the methodology. This is the apparatus that we use, which is like multi-tube manometer, orifice plate, nozzle, water inlet, main switch box, flow control valve, white and also black color ventilation valve, rotometer, gate valve, water outlet, venturi, and also some tank. And this apparatus will be used to carry out the experiment of the flow measurement test. This is the procedure. So at first we need to ensure that the orifice plate was properly placed at its position and fasten the manometer tube H1 and H2 to the orifice plate. And step 2 will be to the flow control and also gate valve need to close, and then the main switch and the pump need to turn on. Simultaneously, the flow control and the gate valve was slowly open until they reaches the maximum opening level. And the ventilation valve black color was opened by turning it to anti-clockwise direction to release all the bubble in the system if any. And the black ventilation valve was closed, and also the gate valve was closed, pump also turned off. The ventilation valve white color one will slowly open until the minimum water level of 30-40 millimeter was reached, and then the pump was turned on. The gate valve was slowly opened until the level of water in H1 reached maximum 390 mm, and manometer was at minimum level. All the reading was recorded at this moment. Okay, and all the reading for 5 different value of actual flow rate by adjust and reduce the opening of the gate valve was recorded also. And the gate valve was closed and the pump was turned off. The manometer tube H1 and H2 was removed from the orifice plate. Orifice plate was changed with the nozzle, and step 1 until step 9 was repeated. Meanwhile, for the venturi, the manometer tube was connected to H1 to H3, and similar step of step 1 and also until step 9 was applied. After finish, all the manometer was removed, the flow control valve was closed, the main switch was turned off. So that's all for this methodology.
Okay, now I will present for result and discussion. Okay, first, for the result, okay, for orifice plate, first we need to find the cross-section area of pipe with the diameter of pipe given. The formula is A equal to pi r squared, and then we need to find the cross-section area of the nozzle with the diameter of nozzle given. And then for the table, the first column equal to Q rotameter, which is in liter per hour, and then the second column is volume water collected in liter, this is time per second, and then Q actual, The formula is volume of water collected divided by time. And then Q theoretical, which is the formula is A2 times with 2G times with delta H divided by 1 minus power of A2 divided by A1. And then this is H1 and H2. Delta H is represent the difference between H1 minus H2, and then CD, which is represent the coefficient of discharge. Okay, this is for nozzle, and then this one for ventilator. The table is also same with orifice plate and nozzle. Okay, next for the discussion, question 1. We need to find the difference of water level in ventilator with different types of flow meter. And then we need to relate our answer with pressure loss associated with the types of flow meter. Okay, for orifice plate, first and foremost, we need to plot the graph. For the y-axis is equal to water level of manometer, and the x-axis is equal to the flow rate of water. The blue color represent H1, red color represent H2, and the green color represent the delta H. From the graph, we can see that when the flow rate of water is increased, the water level of manometer, which is H1, is increased. For H2, when the flow rate of water is increased, the water level of manometer, which is H2, will be decreased. And for the delta H, as the flow rate of water is increased, the delta H will be getting bigger. And the drop value of H is caused by the head loss of the orifice plate. For nozzle, you can see that from the graph, when the flow rate of water increase, H1 will be increased. For H2, when the flow rate of water is increased, the H2 will be decreased, and delta H will be increased when the flow rate of water increase. And the drop in water level of manometer is based on the head loss of nozzle, which is change in diameter. And the last one for ventilator, as we can see that H1 will be increased as the flow rate of water increase, while H2 will be decreased as the flow rate of water increase. Okay. The increase of difference between two values is because the decreasing of area from H1 to H2. Okay, based on the graph, you can see that H1 will always higher than H2. It is because H1 represent the maximum water level and H2 represent the minimum water level. And the most significant from this experiment, delta H is for ventimeter. It is because the area of ventimeter is the largest, and it will cause the drop pressure due to head loss. Okay, we take that the mass flow during the whole closed pipe should be constant, and when the area of pipe is decreasing, the velocity of pipe will increase. So the pressure drop will be occur. Okay, we can see that from the Bahari equation, which is the formula is P1 divided by rho g plus B1 squared divided by 2g plus Z1 equal to P2 divided by rho g plus B2 squared divided by 2g plus Z2. We consider Z1 and Z2 is equal to 0 because it is horizontal, and the new equation will become P1 plus rho g plus B1 squared plus 2g equal to P2 divided by rho g plus B2 squared divided by 2g. And then according to equation, Q equal to AB, where Q is the volumetric flow rate and A is the average velocity of flow, and V equal to the mean velocity. Since A2 is smaller than A1, so V2 will always higher than V1. As the V2 is higher than V1, the pressure loss is occur, which is P2 is less than P1. In order to balance the Bernoulli equation, so it is proved that H1 is always greater than H2. Okay, from this, it can be concluded that the pressure will be higher at the pipe with a bigger flow area, which is in a lower velocity, compared to the pipe with smaller flow area, has a higher velocity. I think that's all for me. Thank you.
Okay, today I'm going to explain about the differences in discharge coefficient value for each flow meter and the ranking of the flow meter according to their accuracy. So first, we decided to plot a graph of log Q actual against log delta H. So this is the graph for orifice plate, and this is the graph for nozzle, and this is the graph for venturi meter. Okay. So then we also decided to calculate the average discharge coefficient value for each flow meter. So for orifice plate, we get 0.68524. For nozzle, we get 1.05353, and for venturi meter, we get 0.94385. So the discharge coefficient value is important because it determines flow meter's accuracy and performance. So each flow meter has different average discharge coefficient value, as we shown in the table, 7.24. So this is due to the fact that the Q actual and Q theo is the ratio of discharge coefficient value. The smaller the difference between the Q actual and the Q theo ratios in a flow meter, the higher the coefficient of discharge and the higher the accuracy. The difference between Q actual and Q theo when a liquid flows through a flow meter is highly influenced by the head loss and the friction. This is because a flow meter Q actual would decrease due to the increased head loss or the friction loss. As a result, the differences between the Q actual and Q theoretical grows and the discharge coefficient decreases, lowering the flow meter's accuracy. So we discuss about the results that we obtained. So from the result we obtained in table 7 here, the flow meter that gives the most accurate measurement is venturi meter, because based on our calculation and data average of the average coefficient, discharge coefficient, the value of venturi meter is 0.94385, which is the closest to 1, and compared to the nozzle and orifice plate, the average discharge coefficient value for nozzle is 1.05353, which is slightly exceeding above 1, and some error might be occurred during this experiment. The average coefficient, the discharge coefficient value for orifice plate is 0.68524, which is smaller than 1, so that the actual flow rate is much different from the theoretical flow rate. So the most accurate flow meter is venturi meter, then nozzle, and followed by orifice plate as least accurate flow meter. Besides that, so just now we have showed that we have plotted the graph. The graph also can be a way to find out which is the most accurate measurement to flow meter. So comparing all three graphs, we know that we can see that the venturi meter graph has a rather linear graph compared to other two. The graph were plotted to see the accuracy of the values obtained via the calculation from the experiment. So this can be proven that venturi meter has the most accurate measurement. So now we're going to see the factors that contributing to errors and inaccuracy in experimental data and the possible recommendations to improve the existing results. So based on our experiment, the results, there were several errors affecting the outcome of the experiment. So first and foremost, the parallax error might occur because of the observer's eyes are not aligned with the pointer and scale reading the rotameter or the multi-tube manometer. Next, there must be air bubbles trapped inside the system when conducting the experiments, and ventilation valve was opened for a short time, so the air bubbles did not have time to escape. Then the experiment for each flow meter was held once, which might vary when done repeatedly. Besides that, the water leakage between the tubes and the manometer is due to lack of proper connection. Last but not least, the start of timekeeping is not synchronized and might not be accurately started when the water level of tank reads due to different response time of the experimenter. So now we're going to see what are the modifications we can do to avoid these errors. So to prevent parallax error, the observer's eyes should be parallel to the pointer and scale when taking the reading. Next, we should give enough time for all trapped air bubbles to escape from the device. Besides that, with each flow meters, the experiment should be repeated at least twice to obtain average rotameter and multi-tube manometer readings. Then before entering the lab and performing the experiment, students should read and review the lab manual. To increase the accuracy of time, use digital stopwatch rather than using analog stopwatch or other methods. Thank you.
Hi, Dr. and also fellow friends. My name is Pik Lin. I will be concluding everything in this conclusion. Okay, so the objective of this experiment is actually to determine and also compare the coefficient of discharge for a series of flow measurement devices such as orifice plate, nozzle, and also ventrimeter. So we know that when the velocity of flow rate increases, the pressure in the flow rate also will be increases in this experiment, and therefore it can be said that the measurement devices that we study above actually function based on the Bernoulli concept. And the choice for the measurement devices are actually based on the cost, accuracy, and also how far the real operation obey the ideal flow rate that is steady and also illicit and incompressible. So from this experiment, we know that venturi meter is more precise than orifice plate and also nozzle in the flow meter measurement. This is because the orifice plate and also nozzle they have actually higher deviation than venturi meter when we are comparing between the theoretical and also calculated discharge coefficient. Okay, so for the nozzle, the average discharge coefficient value that we get in this experiment is actually slightly exceeding 1, and which indicates that there are errors happening while conducting the experiment. Therefore, while we are conducting the experiment, we should always aware and also foresee this error that might be happening even before starting the experiment, such as parallax error and also the other error. Because as an experimenter, we should always we need to understand the theory and also understand the procedure before we start the experiment, so that we can avoid problem or maybe issue happening during the experiment. So the error that might be happening is such as parallax error due to the observer eyes when they are not aligned with the scale when reading the scale. Yeah. And also there might be air bubble trap in the system, so that we need to avoid this kind of problem, we need to have more time for the air bubble to escape. And also for example, when we want to run an experiment, we should always run it at least twice or maybe 3 times, so that we can get the average result and also can get a more accurate result. And water leakage also might happen in these experiments because when the connection between the tube and also the manometer is not properly connected. Yeah. And lastly, which is the important one, which is proper timekeeping. So in this experiment, we need to have a proper timekeeping so that the time that we recorded is actually synchronized properly with the experiment. And thus we can actually avoid unwanted issue and also error when we aware, and also we try to avoid this kind of problem during the experiment so that we can get more accurate results. So yeah, that's all for me. Thank you everyone. And here's the reference that we use for our experiment.